So we're starting this year talking about functions in chapter 2, and I like starting off with chapter 2 in this class because it's all familiar, or at least it should all be familiar. And what this lets us do is focus on the things that are different with IB, such as the notation and the language and the types of questions, but the content for the most part is something that you have seen before, hopefully in Algebra 2. And if not, or if you forgot, this is kind of your catch-up chapter. This is your chance to make sure your mathematical prior knowledge is up to speed where it needs to be to conquer IB math. So what I want to start with is just some notation that you're going to see. And every so often I'll kind of make these little side boxes over here up in the corner just to highlight some of the notation that we're going to be using, right? It's important that we can speak the language of math, and part of speaking the language of math is understanding the different symbols that we're not used to. So some of the notation that you're going to see, this little ST abbreviation just stands for such that. And this is more just an abbreviation that I use. It is pretty common in mathematics, but it's not something that I've seen too often in IB. So you'll see me use this a lot in my notes, but it's something that you might not come across necessarily in an IB exam, for example. This little fancy looking E is a little bit of set notation, and that's our way of saying that something is an element of a set, or something is in a set. Right, I could say that 2 is an element of the set 1, 2, 3, for example. By the way, just logically, if I crossed it out, that would be saying is not an element. Right, this is just my way of saying is not an element. And then my fancy looking R you've probably seen before. This is just the set of all real numbers. Right, and we've seen this a lot, right? I can say that something is an element of the real numbers, or the domain of a function is the set of all real numbers. But just to start getting you thinking about the notations that you're going to see throughout this chapter, throughout this year, we're going to start right there. So let's start with some definitions that should hopefully be review for us, starting with relations. So relations are just mathematical rules. It's some set of ordered pairs usually, such that my x's in the ordered pairs come from a set, we'll call it A, just as a placeholder. And my y's in that ordered pair come from some set B, again, just as a placeholder. And this is kind of a formality here, but A and B should be non-empty. So this is really being stated just to make sure that x and y are actually coming from somewhere, and we're not just kind of plucking it out of thin air and choosing it randomly. Right, so I could kind of come up with a relation, or it's just any kind of mathematical rule, right? And it maps maybe 2 to 3, and 3 to 1, and 1 to 2. And that could be my relation, right? I could express that as a set of ordered pairs, right? 2 goes to 3, and 3 goes to 1, and 1 goes to 2. And that's just a relation. Nothing fancy, it just maps one thing to another. And a function is a specific type of relation, and the catch that makes a function, or a relation a function, is that every x value has a unique y value. Right? I don't have any sort of cases where one x goes to like two different y's, right? That would not be a function. Every x has its own unique y. Actually, my example that I came up with right here would be a function. And a function has domain and range. And this should be familiar, right? Domain, with our new notation d sub f, so d for domain, is the set of x values, and the range r sub f is the set of y values. And sometimes we'll actually call x the independent variable because we can change it independent of any other variable in the function. And y is often the dependent variable because its value depends on what input x that I'm putting into the function. That sounded really complicated, and it's not. Right? If I think about a function as a machine, we'll call that machine f. And maybe my function is the doubling machine. Right? So my function, I'm going to take some kind of an input, x, right, from my domain, and it's going to spit out some output, y, which in this case is twice whatever I put in. and that would form, the set of all those outputs would form my range, right? We kind of know this already. If I put in 3, I get 6. If I put in 5, I get 10, and so on. Right? My y's are dependent because they depend on whatever x I put in, but I can choose whatever x I want, which is what makes it the independent variable. So just to summarize, a relation R is a function if R acts on all elements of the domain, and R is what we call well-defined, so that each element of the domain maps to one and only one element in the range. So each element of the domain maps to one and only one element in the range. Fancy way of saying this is just to say that if f contains 2 points, we'll call them a, b1, and a, b2, or if you prefer numbers, we could say 1, 4, and 1, 5, right? This can't be true, right? The example I came up with cannot be true because I have one element in the domain mapping to 2 different elements in the range. So if I have 2 supposed points with the same x value from the domain, then my y values must be the same. That's all this is saying. So a little more fancy notation here. If y is a function of x, then we already know this. Y can be written as f of x, right? Function of x. Or this might be a little bit new. X maps onto f of x. Sometimes you'll see this where we actually state the domain and range that this is coming from. So maybe I have a function, my name of my function is going from real numbers to real numbers. So I'm putting in real numbers and I'm getting real numbers out. And I'm taking my input and whatever's happening, it's doubling it. So this is kind of like my machine up here. Well, instead, I'm writing it out this way. So you can see it this way. Right? I could have also written this as f of x equals 2x. And then I can look at all my inputs. Or yeah, so if I put in 3, right, 3 is going to map onto 6. Pi is going to map onto 2 pi, and so on. And just another notation that we're going to see kind of in general, especially throughout this chapter and beyond, is this IFF, or if with another f after it. IFF just means if and only if. So if and only if. And all that means is that the sentence works both ways. Sometimes in logic you'll see this double arrow, which helps us to remember that you can see this both ways, right? If and only if means x if y and y if x. You can read the sentence forwards and backwards and it means the same thing. So for example, our vertical line test, which is something you've probably seen before. If f is a relation, it's a function if and only if a vertical line passing through the graph of f never intersects the graph of f at more than one point. Right, so here's that if and only if, which means I can read it both ways. If I take a graph and I pass a vertical line through it, and I never cross at more than one point, then it's a function, and vice versa. For example, on my left here, it doesn't matter where I draw this vertical line. I can draw a vertical line wherever I want. I'm only ever going to intersect this graph once. This is a function. On the other hand, on my right, if I draw my vertical line, and I can draw it in a number of places, and I hit it twice. I hit the graph twice. It doesn't matter that I could theoretically draw a line here and hit it once. That's great, but we still have a case that makes this rule fail, and so therefore we're going to say it is not a function. So if I have a function, I have domain and range, and I want to be able to talk about what domain and range is. We can do this in a number of different ways, and we'll use both of these ways interchangeably throughout the year. The first is in set builder notation, and this is kind of what set builder notation looks like with my fancy curly brackets on the end. I have a number of things. Most importantly, it is a set, which is why I have these curly brackets. So curly brackets means we're talking about the set of something. Well, it's the set of whatever variable I'm talking about. And I want to know whatever the number set of the domain is. I'll clarify that in a minute, but that's things like real numbers, integers, natural numbers. Maybe you're even just talking about a specific interval. This bar is an even shorter shorthand for such that. And then over here, I have some kind of condition. I want to talk about this number set again because, just as everything in math, we have a catch. And the catch is you may leave out if x is an element of the real numbers, right? So actually I could simplify this and say x such that x is greater than 1, and it's implied that we're talking about the real numbers. So that's just kind of where we're going from here. If my domain or my range is an entire number set, so maybe I wanted to just talk about the real numbers, then it's a little bit redundant. I'm just actually going to say x such that x is a real number. Right? I can do this with the integers. I can do this with any sort of number set. But this is kind of my special thing for if we're referring to an entire set of numbers. For example. So that's kind of what we're talking about with set builder notation. And this is something that they would prefer when we're talking about domain and range. In interval notation, first of all, interval notation assumes that we're dealing with the real numbers. My open bracket or my parentheses implies that we're not including the value. Right, so for example, if I said 3 less than x less than 4, I can just write this as 3 comma 4 with the parentheses to tell me I'm not including those. With my brackets, my closed brackets, that means that we are including them. Right, so if I were to change these to like less than or equal to, they just turn into brackets. I'm including those numbers. And then my U for union, this is more set notation. And that means I'm joining two intervals together. For example, I could say maybe the numbers from 3 to 10, including 10 but not 3, but also the numbers from 15 to infinity. And I'm actually glad I brought this up because one of the things about infinity is that plus and minus infinity always take parentheses. So just a couple notes here. If the domain and range are discrete sets, meaning there are like specific numbers, you could list all the elements, right? I could just say that the domain is 1, 2, 3, if that's the case. If the domain and range are an entire number set, we still have to use the whole structure, and that's kind of what I talked about up here, right? To say that if I'm talking about the whole set of real numbers, I'm going to write it this way. I'm not just going to write this. I still need to kind of introduce my variable first. I want to say, all right, we're going to talk about x or y or a or whatever, but I still need to introduce that number set in that variable. So these notations can be a little bit tricky at first, but they do come naturally once you kind of get used to writing it. It's like anything else, right? With a little bit of practice, it becomes second nature, and you're going to be using this a lot throughout the year. So you will have plenty of practice in using it. So just to review a couple examples, we want to know if these are functions. If they're functions, we can state the domain and range. With number 1, I always prefer when I have ordered pairs to list out my numbers. So if I look at x and f of x, I see 2, 3, 2, and 1. And I see 3, 4, 1, and 4. And we already have a problem, right? Because I said that I can't have an x value be mapped to more than one y, and that's what I have here. Right, this is a problem. So this is not a function. The second you see a duplicate x that is going to two different y's or just more than one y, then you got a problem. And then it's not a function. It's just a relation. On my left here, with a graph, you can just think about the vertical line test, right? If I were to, let me see if this works. If I were to take a vertical line and I were to pick it up and drag it through my function, at no point in this function do I hit my graph in more than one place. And you might be asking, well, what about this? Right? Well, this open circle tells me that there's no function value there. It's the closed circle that I'm going to go for, right? So this would be the actual function value at whatever that number is. So this is a function. And just to be able to do the rest of this, let's call this number -1. So I want to know the domain. Well, the domain is all real numbers, right? This graph continues on and on forever. There are no gaps, there are no holes. Well, there is a hole, but not in the x's, right? Every x has a value. So it's just x such that x is a real number. That's just it. And with the range, well, we just have to take a look at the graph. And keep in mind with the range, we're dealing with y's, not x's. So y such that, well, if I'm looking at my range, I have values from -1 and up. We're going to assume that this is just human error here, and it actually does hit -1. So this isn't all real numbers because I don't have graph down here. I have graph from -1 up. So all my y's, and because it's the real numbers, right, I don't need to state that it's a real number. We're assuming that it's a real number. And it's all of the real numbers that are greater than or equal to, to -1. And I'm just going to state that, just like this. And that's all I'm doing. That's all we're doing with domain and range. Again, a lot of this, the concept itself is probably review. But some of the notation might be new, some of the terminology might be new, which makes this section a great way to start off your journey in IB.